A uniform cylinder is made to rotate about an axis of rotation that's parallel but offset to its longitudinal axis. This black line represents the longitudinal axis of the disk, and this red line represents the offset but parallel axis of rotation that the disk rotates about in this situation. The red dot you see here represents the axis of rotation. This is a rough animation, not an accurate physics simulation. You should see the disk attaining a zero angular velocity when it swings all the way to the left or all the way to the right. You should also see a maximum angular velocity at the bottom. This gives you a rough idea of what's going on. Okay, so this is a job for the parallel axis theorem. Here's my derivation of the parallel axis theorem that I provide via my YouTube video lecture notes. I very closely follow the steps provided in the Halliday and Resnick textbook, and here's the parallel axis theorem. ICM represents the rotational inertia about an axis of rotation going through the center of mass. M represents the object's mass, and D represents the offset distance between the center of mass axis of rotation and an offset but parallel axis of rotation. Similarly, here's the derivation I provide via my lecture video for the rotational inertia of a uniform solid cylinder. Again, I stick pretty much to what's provided in Halliday and Resnick, and after 12 fun steps, I provide the expression for the rotational inertia of a uniform solid cylinder. So for part A, to find the rotational inertia of the cylinder about this new offset but parallel axis of rotation, it's pretty much plug and play at this point. My disk mass is 20 kilograms, the disk radius is 10 centimeters, the axis of rotation is offset by 5 centimeters, and I plug in the numbers and get 0.15 kilogram meters squared. Part B is asking what the angular speed of the cylinder is as it passes through its lowest position. So you take the cylinder and you rotate it about its offset axis of rotation so that this axis of rotation is at the same height as the longitudinal axis. The red line is at the same vertical height as the black line. Then you let go and the cylinder rotates about the offset axis of rotation, and your job is to figure out what the angular speed is at its lowest position. Step 3 says to take a conservation of energy approach. So in step 4, I'm asking what is the total energy at state A, which is this top position starting from rest, plus whatever non-conservative work is done by non-conservative forces. And that equals the total mechanical energy at state B, which again is when the cylinder is at its lowest position. The kinetic energy at A is 0 because it's starting from rest. The gravitational potential energy at A is 0 because I'm just defining that as my baseline. There is no non-conservative work being done by non-conservative forces, so that term disappears. At energy state B, I do have some kinetic energy. This is the cylinder at its lowest point, and I do have a non-zero gravitational potential energy term. This is my expression for gravitational potential energy. This is my expression for rotational kinetic energy. So when I solve for omega, I get 11.43 radians per second.